Thanks to the organizers for giving me the chance to speak here. It's been a great conference so far. Gotten to learn a lot. So as Annika said, I'm going to be talking about a systematic EFT approach to SIDM. That part of the talk is based on these two works here. And then the astrophysical implications is going to be some work to appear that's being spearheaded a lot by an excellent graduate student, Duncan Adams. So just to get started, since this is a dark matter conference, I don't need to convince you that dark matter exists. But the question then is, why do we think about SIDM, right? And going back, oftentimes it was cited as a way of solving some small scale issues and things like that. But as a theorist, I like to take a step back, right? And I like to look at a standard model, which has a rich structure. It has, multiple product gauge groups. It has lots of different fields, and all of these fields interact. They all have non-trivial interactions. But it also makes up a small part of what the entire universe's energy budget is made out of. So it seems very natural to expect that maybe the dark sector has some rich dynamics. And if that's the case, we need kind of a systematic EFT approach to figure out, what can happen, right? And so just to kind of set the scene a little bit here. So this was a paper that came out, a while back, but it was basically looking at different systems such as dwarfs, LSBs, and clusters, and essentially backed out what kind of the cross-section should look like to explain the density profiles that you would see in these objects. And just by eye, you can, they fit long-range Yukawa potential, but even by eye, you could see that maybe I can draw different curves that go through this, right? And so the question is, what are the curves that I can draw, right? Can I just draw whatever I want and find a model that fits it? Or is there some more, are there constraints on the types of things that I can do? And the other thing to note here is that the velocities of the dark matter are very low. And so here you might have to worry about Sommerfeld enhancement, right? So to explain what Sommerfeld enhancement is, I feel like a classical analogy is actually a really good way of kind of building up this intuition, right? So imagine you have a disk of radius r and a small test particle that's moving at some velocity v. If you don't have any kind of attractive force or any kind of attractive behavior between these two objects, then the cross-section is just going to be pi r squared, right? Just the cross-sectional area of that disk. But now imagine you turn on gravity. So imagine, this is the sun, it's a radius r, your little test particle is a comet that's moving at some velocity v. You know that the cross-section actually goes like pi times some impact parameter squared, which if you rewrite it in terms of velocity, has this behavior, this 1 over v squared behavior, right? And what that tells you is that when you're moving at velocities that are low compared to the escape velocity, so when you're moving non-relativistically, you're going to get this enhancement, right? And intuitively, this sort of makes sense, right? If I have a comet that's just zipping by the solar system, it's not going to deflect a lot. But if it's moving very slowly, you're going to start getting large deflections in kind of the orbit of this object. So to build intuition, this classical analogy is useful, but more concretely, what exactly is it, right? So it's a non-perturbative effect. So for my fielders in the audience, this means that you're basically summing up an infinite series of ladder diagrams that's relevant. And once you do the sum, you end up actually getting this enhanced cross-section that you see. And in field theory, this is a prohibitively difficult calculation to do. But there's a really nice simple mapping to quantum mechanics where you can take the tree-level process in field theory, map it onto a quantum mechanical potential, and once you solve the Schrodinger equation and take out what the S matrix looks like at infinity, more or less, you can actually do this entire resummation, using that procedure. So as case studies, we're going to look at two. So the first case study we're going to do is scalars. So this is the Yukawa potential. This is the same thing that was used to draw that curve on the first slide that I showed. And the other one we're going to do is a pseudoscalar, which is this gigantic, horrific mess, and it traumatized me for probably a year and a half. But now I've grown to love this potential. And it has sort of two important things to kind of point out. One is there is a non-trivial operator structure that comes into play here, which you notice is missing in the scalar case. And the other thing is that it has a 1 over r cubed behavior. Now, for those of you who have either taken or taught quantum mechanics somewhat recently, or any kind of math methods class, you know that if you try to set the boundary conditions at the origin, so if you try to set boundary conditions at r equals 0, for a potential that goes like 1 over r cubed or diverges, essentially any faster than 1 over r squared, it's not possible to set well-defined boundary conditions and have a well-defined differential equation at the origin when you do this, right? So the question is, how exactly do we deal with this? And this is where the intuition from thinking about effective field theories below certain energy scales and matching kind of comes and saves us, right? So what we want to think about is basically breaking apart our region into two different regions. So there's this R less than A region, where A is a proxy for the Compton wavelength of the dark matter particle you're scattering. And then there's the R greater than A region. So when you're less than the Compton wavelength of the particle, you should expect that the particles are semi-relativistic. And specifically there, you should expect that quantum mechanics should be a bad description of what's happening, because that's the low velocity non-relativistic limit of what's happening, right? So what we want to do is somehow leverage the field theory information here, use that to set the boundary conditions at R equals A instead of at R equals 0, and then do the long-range behavior here, which you know is going to be low velocity, it's going to be well described by quantum mechanics, and you can take into account a lot of the long-range effects like Sommerfeld enhancement. So that's all well and good. How do you actually set these boundary conditions, right? And so one of the really nice things about quantum mechanics is that at tree level in quantum field theory and the first Born approximation in quantum mechanics, these two things faithfully reproduce each other, right? And this is shown here in the plots on the right. But more or less, the idea is that you can actually do this computation. I can cheat a little bit and do this computation in quantum mechanics just to make my life easier. And this K matrix here is just kind of a generalization of the phase shift when you think about scattering. It's just a multi-partial wave kind of generalization of this story. And the idea is that I can do this integral from 0 to A, so 0 to the Compton wavelength of the particle. And that captures all the physics that's occurring in that regime. And then I use it to basically alter the wave function and its derivative. So that gives me the boundary conditions at R equals A. And then I can solve the Schrodinger equation moving outwards from there. Right? Okay, so I've set up all of this, all of this behavior. Now the question is, let's actually do some numerics, right? So in the scalar case, here are the numerical results. So in blue is this numerical cross-section. So this is computed using this entire prescription that I just, spent the past few slides describing. And in orange, I'm just taking the tree-level process in field theory. And I'm just saying that I'm not actually going to do any kind of resummation, anything fancy. I'm just going to take the tree-level process. And, as a naive, field theorist, you would say that if my theory is perturbative, this should be a good description, right? And what you find is that at low velocities, you see a very clear enhancement. And this is exactly the Sommerfeld enhancement that I was describing. And then at larger velocities, you start seeing that these two curves start to coincide with each other. And that's kind of telling you that the Sommerfeld enhancement basically shuts off as the velocities get higher and higher. And it's good enough to basically suppress these extra loop diagrams that I've been talking about, right? Now, one other thing that I haven't talked about is that the scalar exchange, or Yukawa potential in general, I'm using them interchangeably, it's actually a problem where you can actually define the boundary conditions at the origin. And this is how it had been done in the literature prior to the matching prescription we developed. And what you end up finding is if you do it that way, where you just set the boundary conditions at the origin and don't think about our matching prescription at all, you actually reproduce exactly the blue curve. So that tells you that this matching prescription that we developed using our intuition from effective field theory matches onto what you would have expected. And that allows us to then start thinking about the pseudoscalar potential, right? Here you don't have this liberty of just setting the boundary conditions at the origin anymore. Here you need to actually do this matching prescription. And so again, using the same kind of color scheme, blue is the numerical cross-section and orange is the tree-level QFT cross-section, what you end up finding is that there's actually no Sommerfeld enhancement at low velocities. And then at high velocities, this deviation is about a 1% deviation, and that's exactly saturated by the fact that the potential that I took to compute this process numerically was leading order, and the next order correction in the potential is going to scale like order beta, which in the cross-section scales like beta squared, which would be 1%, right? So, this may seem surprising, but we can kind of understand this heuristically, right? So effectively, this is a short-range potential. So the 1 over r cubed and the 1 over r squared pieces basically fall off too fast to kind of have any sort of long-range behavior that would be necessary for generating, any kind of enhancement. So then that leaves the question of, there's a piece like this that scales like 1 over r, and likewise a piece like this that scales over 1 over r. So you might ask, why are these pieces not generating any Sommerfeld enhancement? They have the same functional dependence as the Yukawa potential. Why aren't they generating any dependence? And so the reason for that is A potential will be long range when m phi is light, in particular when m phi is light compared to m chi. And that's precisely where these terms shut off, because they're suppressed by m phi squared over m chi squared. And so in general, basically the pseudoscalar potential behaves like a short range potential. There's a much more rigorous way of actually deriving this, and you can do this using Feynman diagrams, right? And so at tree level, there's two contributions that come in. There's the S and T channel diagrams. And at one loop, there's diagrams like this box diagram which come in. And basically what we want to do is take this ratio of the one loop to the tree level diagram. And what you end up finding is that the scale's like a naive log of the mass ratios, which can be resummed like what are often talked about as pseudocov logs. But this is a behavior that can be resummed, and you actually don't end up finding any enhancement. As opposed to that, when you look at the scalar case, you end up finding that the ratio scales like alpha m chi over m phi. And that tells you when m phi is less than alpha m chi, you actually get this enhancement. And this is exactly one of the conditions that's stated in the literature for when Sommerfeld enhancement is important. Right? So, now that kind of begs the question of, like, we started off this talk and I told you that one of our acute potentials are, nightmarish and they're kind of ugly looking. Are they singular? Do they actually have any kind of importance? And, what I can argue, and, we can talk more offline, is that the pseudoscalar potential is actually not singular. And more importantly, people in the literature have claimed that singular potentials have importance for phenomenology, specifically Sommerfeld enhancement and SIDM. And I'd argue that if this matching is done carefully, you end up getting a potential that's A, not singular, and B, you end up getting some, behavior that gets completely regulated by the nature of the underlying theory that you're matching to. Okay? So enough theory, where's the astrophysics, right? I told you there's going to be some astrophysics in the talk. So the first thing that I want to kind of, use this to lead into with the astrophysical side of things is gravithermal collapse, right? So anytime I have this self-interaction cross-section, if it is strong enough, and in particular, velocity-dependent cross-sections tend to be stronger at lower velocities, so lower mass subhalos in general will be more susceptible to a process like this. You end up going through this process of gravithermal collapse. So I'll kind of just quickly walk you through, what happens. And, I'm describing it here for an initially NFW profile, but, this has been shown to also hold for truncated or tidally stripped profiles as well, right? And so what happens is, first, you have self-interactions that are occurring in the inner region. They start to thermalize that inner area. And they increase the temperature, and it forms sort of a gradually expanding core. And then at some point, this expansion halts, and it turns around, and that's the onset of core collapse. And then this core starts becoming denser and hotter as it shrinks in size. And eventually, you'll then go into the short mean free path regime, and at that point, the core is kind of optically thick to these dark matter self-interactions. You sort of reach its maximum mass, and then the density and temperature will kind of increase rapidly in this phase. But what this tells you is that if I have a velocity-dependent cross-section specifically, halos of different sizes will be at various points along this, collapse sequence. So we've heard a lot of good talks, over this week about using streams as detectors, and that's kind of the, the angle that we're thinking about this problem from as well. And we want to basically use streams as a way of, essentially detecting both, being open to detecting the subhalo mass function, as well as, if we're lucky and we have interactions that are occurring very head-on, we may even be able to start kind of probing the dark matter density profile of the subhalos that are, that are interacting with the stream, right? And I've taken this plot from on this paper. It's a really great schematic that's showing, a lot of the streams along with kind of where they are, their length, and their rough thickness. And, we had talks from Tongyan that told us, what, depending on how thick the stream is, what kind of masses we can be, possibly observe and things of that nature. But as a theorist, I like to make things simple for myself, and I like to take, really simple ideas. So we start with, this very toy schematic of how the Milky Way works, right? We have the galactic center here. We have a nice little dark subhalo that's orbiting, right? And there's many of these. And after lots of discussions with people here, I've learned that schematically, streams look like this. Yeah, I got little stars here, they're thick. And so what we do is we define, that's why I asked you for your slides yesterday, Francis. So what we do is we define, in general, a coordinate system that's relative to the stream, right? So there is kind of this perpendicular direction, parallel, and kind of orthogonal, which is coming out. And what it does is, if we take any subhalo that's orbiting in the Milky Way, and we kind of walk it through its orbit, we can actually compute as a function of where you are on the stream, the type of velocity kick that you're imparting on the stream. And that's coming entirely from the fact that there's gravitational interactions between the dark subhalo and the members of the stream, right? And so you can look at these kick curves that look something like this in the various dimensions. And in general, you can sort of expect that these perpendicular direction ones are going to be the things that kick part of the stream up and this part of the stream back, and they might form spur-like objects. Likewise, the tangent parallel ones are the things that are going to kick part of the stream this way and part of the stream that way, and that can form gaps, things like that. And so what I'm going to do is I'm going to focus on these types of interactions that tend to be very, very large in the velocity kicks that they're imparting on the stream. And so just focusing on the radial and perpendicular one, or the radial kick curve for now, we can basically characterize this curve by essentially two variables, right? So there's this delta mm, which basically takes the peak and the trough and finds kind of the difference between them. And then there's this f peak, which is a way of determining just how concentrated this interaction is, right? So a large f peak would mean that this curve is very spread out, and a small f peak means it's very concentrated at a particular point. So these two variables characterize the velocity kicks that are imparted by the perturber. And if you impart these kicks on the stream and then walk it forward through its evolution to today, you end up finding that there is some sort of behavior where you kind of see, it's a little bit hard to see by eye, but there is a little bit of a kink in this stream here, and there is an underdensity in that region. So you're starting to form kind of what looks like a gap. Right? And so now the question is, what are the distributions of these variables, right? So how many such events do you expect to see? What types of delta MMs and F peaks are sort of expected, and things of that nature. So, the cherry-picked event that I did here, just to make things easier to see, lies down here. But in general, this is where the power of semi-analytics comes into play, right? So these semi-analytic tools, they initialize and generate, various Milky Way-like realizations. And essentially, it just gives you all of the kind of relevant information. It does the orbital information. It contains information about the mass evolution, the concentration, all of these things that are relevant for understanding what the population of dark subhalos look like, or just in general, the subhalos in the Milky Way look like. And it allows us to run lots of samples very quickly, right? So I can run over essentially hundreds of Milky Ways over the course of a week, and I can do this locally. So it allows us to, sort of combat certain effects, like there might just be variance related to the fact that you only simulated one halo. Well, if I run over 100, I should hopefully beat that down, right? And it allows us to marginalize over various, things like there's uncertainties in what the mass of the disk of the Milky Way is, and it allows us to kind of vary those parameters, or the overall mass of the Milky Way halo, and look at the effects of these behaviors, or the behavior of these effects. And in general, the point is that performing these robust population studies is crucial in basically assessing whether the CDM effects can actually produce these features. And so just to kind of summarize and end here. With SIDM, we need sort of a very systematic way of, doing these computations, right? And using kind of our intuition from effective field theory, we can use kind of this QFT to set the boundary conditions at finite radii, and that allows you to basically look at a variety of different potentials and analyze them. And for pseudoscalars, you find that there isn't Sommerfeld enhancement. And it kind of tells you there's a more general story, which I've explored, is that field theory tends to produce these potentials that are very, very non-generic. And so, with this application to SIDM, we might potentially be able to use that as a way of affecting the dark substructure. And the one thing that I wanted to really hammer home is that, just to make things a little bit obvious and easy to see, I've only focused on those kind of rare interactions that are very close in impact parameter and cause large kicks. But there's actually an entire population of things that are very, that are perturbing the stream, but only very slightly, and it leads to kind of essentially like stream heating. And the way that we're going about doing this analysis allows us to, consistently include that as well. So, thank you.